Okay, good morning, everybody. We're going to start out by looking at stuff we did yesterday, the day before, and now just use that to push into today's stuff. So we're going to start by looking at the do now and looking at Charles' law, Boyle's law, and Gay-Lussac's law, which we looked at with a couple of examples yesterday. Pause the video in a second and just draw a little curve for yourself. Label the axes, see what was being interacting with each other, temperature, volume, and pressure, and what kind of combinations, and draw me a quick little diagram, a quick little graph, I should say, for how those lines look. So those are your notes. Flip back a page and fill those out, and then restart the video. We'll see what you came up with. Okay, so hopefully you checked your notes. And remember that Charles's law was the guy with the hot air balloon. It related temperature and volume. As we raise the temperature, the gas heats up and expands, so the volume gets larger also. And that was a direct relationship with this straight diagonal line going up from bottom left to top right. That was Charles's law. Boyle's law was the one that related pressure and volume. That was where we had the marshmallow vacuum chamber. And that's going to be an indirect relationship. So as one increases, the other decreases. Increasing the pressure either forces the gas to be smaller into a smaller space, or changing the volume. If you lessen the volume, you can, same thing, kind of have it in a smaller space and increase the pressure. Or if you give greater volume, you increase the volume, things are not going to be as packed in and they should have less pressure. But that's an indirect relationship when the line kind of slopes downward gently from the top left to bottom right. And the last one, Gay-Lussac's law, looks a lot like Charles's law. This was temperature and pressure. That was the hand boiler. The heat from my hand heated up the gas, which pushed down the liquid and forced it up the tube to the top part of the bulb. So looks a lot like the other one, another direct relationship with the line going from bottom left to top right. And we had those couple of examples we talked about. Now, it would be great if we could just look at these three laws and say, okay, let's cut right to the chase. Let's use some real numbers. Give me something I can work with here. Because we really didn't look at specifics for these things. If only we had some kind of way to put them together, maybe to combine them into something like this right here. It's going to be the combined gas law. So that's what we're going to look at today. It's on your reference tables, and we'll see what that actually looks like. These three equations here, V1 over T1 equals V2 over T2, P1 times V1 equals P2 times V2, P1 over T1 equals P2 over T2. They're individual equations relating to those three gas laws. So the first one, Charles's law, where it's volume and temperature. That's how volume and temperature are related. Boyle's law in the middle was volume and pressure. And then Gay-Lussac's law on the right was pressure and temperature. So these are your three gas laws right here, but we don't need to know each of these three things. It's a waste of time to know each individual law, each individual calculation and equation. We can just put them together. So this right here is the combined gas law equation. This here at the bottom, this is on your reference table. It's on the back page. It says combined gas law equation, and this is what we're going to focus on. This is all you need to worry about. You don't need to memorize anything. It tells you exactly what it is. But this combined gas law equation is going to show you how gases can change their properties. So if you have a single sample of gas, you have some kind of gas in a container, and you know what its pressure is, you know what its volume is, and you know what its temperature is at some initial set of conditions, that's your first stuff right here. That's your P1, V1, and T1. You have a sample of gas, you know what the pressure is, you know how much space it's taking up, and you know what temperature it is. And then you're going to say, okay, well, something's going to change about this. I'm going to change the pressure, I'm going to change the volume, I'm going to change the temperature. Something's going to change, and that will now result in this new set of conditions on the right. P2, V2, and T2. This could be you take your sample of gas after you know what it's like, and you suddenly heat it up or cool it down. You could put it into a smaller or larger container and change the volume. You could put more or less pressure on it. It could be any combination of those things. It could be more than one thing happening at a time. But we'll be able to see exactly what's going to happen to each thing. We'll have to have most of these numbers, and then you're just going to look for the one you don't have. So there's going to be one variable you're looking for. Take the others and find what's missing. Before we get into the real math, we have this STP table on the front page, table A. It tells us our standard temperature and pressures. Standard pressure can be either 1 atmosphere if you're using the ATM units, or 101.3 kilopascals if you're using the KPA units. It can be either one of those things. But standard temperature for these equations we're doing has to be in Kelvin. So you can't use a Celsius temperature. If any of these questions you ever see a question like this and it's in Celsius, you got to convert that to Kelvin first. So you have to add 273 to the Celsius version to get the Kelvin version. I don't believe any of the questions we're going to look at today are going to be in Celsius, but just double check as you're doing any of these questions, read through it, be careful readers, and if you have a Celsius temperature, add 273 to it first, get it in Kelvin, then it's going to work fine. If you try to do it without Kelvin, the math is not going to work out, and you're going to be out of luck. Okay, our first example says a 2-liter sample of gas at 1 atmosphere and 300 Kelvin is heated to 500 Kelvin and compressed to a volume of 1 liter. And it wants to know what is the new pressure of the gas. I gave these steps on the side there. It says just identify your variables. A little chart at the top of the page will fill it in. I just always write on the side of the page for myself, much as we were doing with the heat calculations. I'd write Q, I'd write M, delta T, those things. I saw all of you doing that, showing your work. Keep doing that. You don't have to do any kind of table like this. Just make sure your numbers are there. We're going to figure out what we're looking for. We'll leave it as a variable, either a P or a V or a T. We can get rid of anything that's a constant. So at any point in these questions, we'll see one in a couple minutes, does it say temperature staying constant? You can cross it off. We'll see that when we get to it. If volume or pressure are staying constant, we can get rid of them. We can just eliminate them completely from the question. We'll swap in any numbers we have to, and then we'll look at our original question to kind of see how we might round an answer eventually. But we'll get there as we finish up. So back to the actual variables, the numbers in the question. It says a 2-liter sample of gas at 1 atmosphere and 300 Kelvin. That's the first part of the question. Is telling us exactly what our gas is like. We have a 2-liter sample of gas at 1 atmosphere and 300 Kelvin. So we got to plug those numbers in. Liters is volume, so it's telling us our sample of gas to start has a volume of 2.00 liters. Let's see if my pen lets me write on this. There we go. 2.00 is our volume to start. And it says it's at 1 atmosphere. Atmosphere is one of the units of measurement for pressure. So I'll write that up here. And this question happens to be using atmospheres. You may see a question that's using kPa. It doesn't matter. Just go with whatever it is. You're never going to see a question where it mixes them. If it uses atmospheres, use atmospheres. If it uses kPa, use kPa. And it tells us it's at 300 Kelvin. So that's our initial temperature. So we've got these numbers to start out. 1 pressure, 2 for the volume, and 300 for the temperature. All right, now it says that sample of gas is heated up to 500 Kelvin. So it's telling us that our temperature has changed. So I'm going to write 500 for the new temperature. That's our T2. We started at the initial starting temperature of 300 Kelvin, and now our next temperature we heat up to is 500 Kelvin.
Mr. Bruno wishes to remind NHS members that the NHS cake fundraiser is over tomorrow. NHS members are to return their yellow and white order forms and monies to Mr. Bruno by the end of the day tomorrow. If online orders were placed, nothing needs to be returned since the company has all the records of orders that were made.
Okay, so I'm definitely not recording 2.5 minutes more of a slide. So I wish someone had told me there was cake, but apparently not. So hopefully you got some cake, and we'll get back to some math. Cake is nice when you finish doing math. All right, so it's heat up to 500 Kelvin, and it says it's compressed to a new volume of 1 liter. So you're going to change the volume and compress it, push it down, and make it smaller to 1 liter. So our new volume is 1 instead of 2. So our initial volume was 2. Now our new volume is a little bit smaller. Our container must have shrunk, and we heated it up from 300 to 500. And it says, what is the new pressure? So P2 is what we're going to look for. We don't know what P2 is. We don't know what our new pressure is. We're going to look for that right now. We've got our numbers. Let's fill everything in. So I'm going to write my equation out. It's going to be P1 times V1 over T1 equals P2 times V2 over T2. So our starting pressure times the starting volume divided by the starting temperature is going to be equal to the new pressure times the new volume over the new temperature. And we're just going to do some cross multiplying when we need to. I'm going to plug my numbers in. Our P1 was just 1. I'm going to leave out the zeros, the 0.00. We can come back to that with the answer, but I'm just not going to write all those numbers for now, save some space. So it's going to be P1 times V1, that's 1 times 2, divided by the starting temperature, which was 300. And that's going to be equal to our new pressure, which we don't know what it is. I'm just going to leave that as P2, times the new volume, which is 1, divided by our new temperature, which is 500. So now we'll just solve for P2. I'm going to do cross multiplying. I'm going to start over here. I'll do the P times 1 times 300. So P2 times 1 is just P2 times 300. I'm going to write that as P2, P2 times 300 on the one side of the equal sign. And then the other way, it's 1 times 2 times 500. So 1 times 2 obviously is just 2, times 500 is 1,000. And now I want to solve for P2. I'm going to divide by 300 on this side to get the P2 by itself. That's going to cancel out. I'm going to divide by 300 on this side. And P2 is going to be equal to 1,000 divided by 300, which is just 3.3. So just I'm going to look back at the pressure. The initial pressure in the question was rounded to 2 decimal places. So I'm just going to do the same thing here. I'll write as 3.33 as my pressure. I'll round it off to 2 decimal places. So 3.33, I'll write it a little bit down here. a little bit neater, but 3.33. I'll round it that much. So there's my new pressure. We shrunk our volume down from 2 to 1. We raised our temperature from 300 to 500, and that made our pressure go from 1.00 to 3.33. All right, go to the next question. Number 2, and then I'll let you do the rest. I will show you just one little detail from number 4. I'll let you get to that. So for number 2, it says a 2-liter sample of gas, 2.00 liter sample of gas, at STP is heated to 500 Kelvin and compressed to 200 kPa. So look for your verbs. Look what's going on here. It says something's going to be heated up and it's going to be compressed. So we want to look for what the starting materials were, starting conditions, and then what's going to happen after that. So it says a 2-liter sample of gas. That's telling us our starting volume. So 2.00. Let me try that again. It's being weird. Where did my pen go? There we go. Okay, 2.00 is my starting volume. Now it says it's at STP. So remember, STP or standard temperature and pressure. We have to look those numbers up. This is a shorthand that anyone writing this question or reading this question knows. I can go look to the front page of the reference table and see exactly what units that's going to be. So standard temperature and pressure. Remember, temperature has to be in Kelvin. So we look at the Kelvin version of standard temperature, and the reference table tells us that that's going to be 273 degrees. So we write 273 right here. That's my starting temperature. Now for the pressure, you have the option. Is it going to be the kPa units or is it going to be the atmospheres units? And for that, you just got to look at the rest of the question and see what the other pressure says. So this question right here, for the future pressure, when it's going to change, it says kPa. So we'll use that unit. We'll use the kPa version of standard pressure. And that means we're going to use 101.3 as our initial pressure. That's our P1. Okay, so we've got our P1, V1, and T1. And now I want to see what the new conditions are. It says we had this sample of gas, told us the conditions right there, and then it says it's heated up to 500 Kelvin. So that's our new temperature is 500 Kelvin. That's our T2. It was at 273, that's standard temperature, and now we heat it up to 500. And it says compressed now, the pressure changes to 200 kPa. So the pressure was 101.3, and now the pressure is going to be 200 instead. That's our new pressure. And it says, what is the new volume? So obviously we're going to look for V2. We're going to try to figure out what these things are. All right, let me change my ink color and let's get to our things. So we're going to fill this in, and I'm not going to write the P1, V1, T1 because it's over on the side of the screen there. We did that before. I'm going to start to fill my numbers in. So 101.3. Let's hope I don't run out of room here. 101.3 times 2, just write it as 2 instead of 2.00 to save some space again, divided by 273. It's going to be equal to 200, that's our new pressure, times the V2 that we don't know, I'm going to leave it as V2, divided by 500, that's our new temperature. I'm going to do a little bit of cross multiplying. When I do the 101.3 times 2, and then times that by 500, I'm going to get an answer that's 54, I think he's popping up, 54,600. My tablet's being annoying today, but so far so good. 54,600. That's the 101.3 times 2 times 500. That should give you that answer. Nope, I'm looking at the wrong number. Sorry, let me cross that off there. I'm getting ahead of myself. Look at the wrong number in my notes. It's actually 101,300. Sorry about that. 101,300. I looked at the wrong thing. The other number is going to be that other number. So 101,300. Then when we multiply 273 by 200 by V2, that's the other number. So that's where we now get the 54,600. So I had the right number, just wrong place. Don't make that mistake. So 101,300 equals 54,600 times V2. Okay, so we want to get that V2 by itself. We want to divide now by 54,600. That's going to cancel out. Divide this side by 54,600. And that gives us an answer of V2. Our new volume is going to be, I want to make sure I read the actual long decimal because it is kind of a long decimal. So I'm going to type 101,300 to my calculator, divide by 54,600. I have the round off version. So the big answer is going to be 1.8553 311,355. That's what my calculator says at least. I don't want to write this huge number, so I just want to see how I can round this off. And just to check the rounding, I'm going to go back to the original question. We're looking at the new volume, so I want to see how the original volume was written. And the original volume was written right here as 2.00 liters. So I'm just going to follow the same format. I'm going to round it off to 2 decimal places. So I'm going to actually erase some of these numbers right here. And instead of 1.8555 and change, I'm just going to round all this off. And I'm going to round it to 1.86. And that's how I'll write my final answer. The new volume is 1.86 liters. It was 1.855, whatever. So I'm going to round that to 1.86. It's kind of sloppy, but I guess the job done's there. Okay, I'm going to finish this off. I'm going to flip forward to question, I believe it's 4. So I'm going to skip 3. I'll let you do 3. I just want to point something out in question 4, and then you can get to the rest of them yourselves, and we'll finish it off. Process here, get answer, and then I'll meet you at question 4. So one little detail here that's different from other questions. We can set up the same way. It says a sample of gas occupies a volume of 2 liters. So our volume is right here, 2.00 liters. That's our starting volume at STP. We can again go look it up. STP, our standard temperature, is 273. And we want to see which form of the pressure we're using. I see another pressure number written in the question in atmospheres. So I'm going to write the pressure standard was 1 atmosphere. So I'm going to write it as 1.00. Okay, that's our starting conditions. And then it says if the pressure is increased to 2 atmospheres, I'm going to write my new pressure as 2.00 atmospheres at constant temperature. That's an important point right here. If something is constant, it means it's not going to change and we can ignore it. Constant temperature means it's going to stay exactly the same. So if we start out as 273, we're going to end up with the same temperature right here as 273, which means when you put them into the equation, this number here, the T1, and this number here, the T2, they're going to be the same number and they're going to cancel each other out. So we can just entirely cross this whole thing out. And instead of writing P1 V1 over T1 equals P2 V2 over T2, we can just simplify our equation, get rid of these things, and it becomes P1 V1 equals P2 V2. Now, in this example, we knew the temperature was 273, so we could write it twice. If you worked it out with the 273 on each side, that's fine. It's going to work out the same way. But you can save yourself some time and energy and just get rid of that number. Just cross it off the equation entirely. Sometimes you won't even be able to do that. Sometimes the question will just say, here's these conditions. It won't even tell you what the temperature or the pressure is, and it'll just say it's going to be constant. So you don't even have a number to plug in if you wanted to. You'll just have to completely leave it out in general. So in any case, we got P1 V1 equals P2 V2, and we're going to look for our new volume, and that's what we can do here. So now we can just plug in these numbers and leave out the temperatures, and you should get a nice answer for this V2 right here, which is what you're going to solve for. Okay, hopefully you'll be able to follow through with everything here. If not, go back and watch again. You can discuss with your classmates if you need to, but work on these questions. You have 6 questions. We did basically about 2 and a half of them together. Finish the rest of the 6, and then in Schoology you have what says the combined gas law problems. It's 8 more questions. I think it's actually ones that's in your sheet too, but you can work on those, and that'll be all today. Make sure you turn them in with Schoology so I can take a look at them, and on Monday we'll come back and do some other stuff, unless you're watching this on Monday, which you shouldn't be, I think, but on Monday we'll have some more stuff to do, and we'll wrap it up, and I'll see you on Wednesday. Have a great weekend.